In this lecture, we're going to wrap up static analysis and then explore dynamic analysis. I'll introduce you to IDA and cover some of its fundamental features for reverse engineering. We will also explore debuggers, specifically GDB and Linux. When you're analyzing a lot of code statically, it's useful to identify patterns. On the left-hand side, you have the disassembly of a for loop. At first, it may not seem obvious, but when you look at the disassembly in graph mode, it becomes more apparent. Looking at this graph, our disassembly is broken into code blocks. The first block, we're setting up our stack frame. We continue execution into the second block, where we enter the for loop, make a comparison, and encounter a conditional jump. Either we jump left if it's true, or to the right if it's false. We stay inside the for loop as long as the condition is true. Once it's false, we break out of the for loop and return. Over time, you'll develop an eye for these patterns. Here's an example where the disassembly of the code block is not shown, but looking at the graph, we can get a high-level understanding of what's going on. We start with our initial code block. We either jump left or right based on the condition being true or not. If it is true, then we continue executing the second block, which we encounter a second condition. Again, we either error out or continue. This is a common stair-step graph where the program is making a series of checks or calls. So I know that if I want to get to the end of the subroutine, I'll have to provide an input that satisfies these checks. Perhaps I'll enter into this for loop, or it could be a while loop as well, but we know that we're going to enter into some kind of loop. And then eventually I can return the result that I want. All of this would not be clear by looking at the disassembly in text view rather than in graph mode. By zooming in on the graph, we can look at the disassembly. We see that after we make a call, for example, bind here, set sock opt here, listen here, we then compare the return value to 0xFFFFFFF, which is represented in hex, or -1. A -1 represents an error for the called function. So if we encounter this, then the program will exit. So this program is making sure that it is properly setting up its socket for network communication. IDA is a powerful tool for static analysis. It even allows us to simplify our graphs so that we can make better sense of what we're reversing. This is a simplified version of the stair-step example we were looking at. On the left-hand side, you'll see that I've grouped together all the failure cases into one node. You'll see that right here. On the right-hand side, if we zoom in, we compress the disassembly of each code block. For the first block, we collapse the lines of disassembly into a node that we then labeled set sock opt, because the purpose of that block was to make a call to set sock opt. We collapse the next block as bind, the next block as listen, and so on. Now I can quickly look at these blocks and know exactly what they are doing. Now, let's walk through the key checker binary in IDA. We'll be using the freeware version of IDA, which is IDA 5.0. Here we are in IDA. Now let's open up our binary of interest by going to File, Open, and our binary that we'll analyze is keychecker.exe. You're informed that you're opening a Windows portable executable, as notated here. And for the purpose of this exercise, you're going to use the default settings. So we'll go ahead and click OK. We're initially presented with the text section of our binary. If you happen to open directly in Proximity View, feel free to hit Shift minus or Shift plus to drop you back into text view. And as you see here, we're now in graph mode, which is what we're going to utilize within IDA. So if you happen to be dropped into the graph mode and you're still in text view, feel free to hit the spacebar to take you into graph mode. When you run the binary on the command line, it presents you with the string, "Hey, no bypassing me." Then it exits. So let's find where that string exists in the binary. We can come over here to our strings window, which was already shown when we opened up our binary. If it's not displayed, feel free to go to View, Open Subviews, and then you'll see Strings. And as a keyboard shortcut to remember, you can also use Shift F12. So let's double click on this string to see where it's being used in our binary. So here we see, "Hey, no bypassing me," which has this corresponding label, and it also has a cross-reference. So let's double click this cross-reference to see what function it's being used in. And as we see here, "Hey, no bypassing me" occurs in this code block, and you can tell that it is an argument to printf. Not only that, we see that it's also in the company of other strings, which are also serving as arguments to printf. Now let's look a little further into this binary. By simply looking at the call instructions, we see that we are opening a file, which is named keyfile.txt. It is then reading from this file and later closing it. And so based on the strings and the calls that are being made, I'm going to make the claim that this subroutine is actually our main function. So let's rename it to main by clicking on the subroutine label. You can right click, hit rename, or you can use the shortcut by pressing N on your keyboard. Here we can now type in main into the name field, and we'll hit OK. We're also going to set the function prototype. Again, you can either right click and select set function type, or you can hit Y as a shortcut. And here we can actually type in the prototype for main. So we have int main. We know that main can take either 2 or 3 arguments. And let's provide 3 arguments just in case, to make sure our stack lines up correctly. So we have int argc. We have a double pointer to argv. And we also have a double pointer to our environment variables. Okay, now we can hit OK. Interesting. Let's try this again. We got the exclamation, the semicolon at the end. There we go. So now we see that our stack was corrected. I'll go into this a little bit later. But we see that by providing the prototype for main, 3 of our arguments are now properly labeled, now as argc, argv, and the environment variables pointer. So now let's look at the different calls to get a better idea of what type of data my code block involves. So for example, when we were looking at fopen, we know that it takes 2 arguments, right? The first argument being the name of the file you want to open, as well as the mode, such as read or write. So if we highlight by clicking on this unknown variable, we see that it has the ASCII lowercase r, which stands for read mode. This means that fopen will open keyfile.txt for reading. When we look at fread, we see that it takes 4 arguments. Again, looking at the documentation for fread, it's taking a file pointer, so we can provide this as a comment. So we can click on that instruction, and then by hitting Shift colon, we can type in file pointer. We'll hit OK. The next arguments are 2 size t variables, so we'll just notate this as size t. And again, Shift colon brings up the comment box. And then lastly, we have a void pointer, which represents the buffer in which we're reading into. So we'll say void pointer. Excellent. Additionally, IDA will describe the stack of this function, which I touched upon briefly. And as you see here, we know that EBP minus an offset represents the local variables. So you'll see here -8, -12, and so on. These represent the local variables, which are notated as var _8, _c, _10 in hex, and that corresponds to the appropriate offset for that local variable. Furthermore, we know that EBP plus an offset represents its arguments. So EBP plus 8, plus 12, plus 16 correspond to the arguments of main, and again, which are properly labeled as argc, argv, and the environment variables pointer. Now, let's learn more about what our local variables are. If we look at fopen, we know that EAX is the return value of the function, which is a file pointer. This is then moved into the local variable var2c. So let's rename that to something more descriptive, like file pointer. You can right-click and select rename again, or using the keyboard shortcut N. So let's just call that file pointer. And you'll notice that every other instance of that local variable is also changed to file pointer. So if I highlight this renamed variable, I can see the different instructions that are now utilizing this local variable. Now, continuing with the arguments of fread, we see that void pointer, again, which is the buffer we will read our data into, is stored in EAX. But where did EAX previously come from? Well, it came from var28, looking at this previous instruction. So let's rename that to something more descriptive as well, such as buff. By commenting and renaming variables, we have a better idea of what our binary is doing. Now, by looking at the strings of this function, which we notice were down here in this area, we can see that we ultimately want to enter into this code block, which is described by the string, hey, you have the current key, you win. So let's color this node green by going to the left upper hand corner of this code block and choosing a color preference. In this case, I'll choose green for success. The other code blocks, based on their string descriptions, indicate a failure case. So let's mark them red. So I can actually color blocks simultaneously by holding down the control key and selecting multiple blocks. Let's do this. And again, we can select the color node, and since they're a failure case, let's choose red. Okay. Not only that, I can also group together these failure cases. So again, I can do a multiple selection of these code blocks, right-click, and let's say group nodes. And now I'm presented with the opportunity to describe this group node. So let's just say fail. And you'll notice how they were all grouped together, but the coloring went away. So let's recolor this. Red for failure. If you need a reminder of what the group nodes consist of, you can then click the uncollapse icon for more details. This is edit group text, uncollapse group. So I can click that. And again, just as a reminder of what this group node consisted of. And then I can actually collapse them again by clicking the collapse icon. There we go. If you want to get more insight into your binary, the subviews in IDA can be quite helpful. For example, if we look at the subviews, again by going to View, Open Subviews, here we go. I can look at my imports, my exports. I can even look at the permissions of my sections and segments. So let's open that briefly. As you see, we have the names of our different sections, such as .text, .data, .bss, as well as their corresponding permissions. So again, the subviews within IDA definitely provide you with a lot more information about your binary. As you dig deeper into your function calls, say for example, I wanted to, analyze fopen or another subroutine. Let's click this one arbitrarily. I want to be able to navigate my binary easily. So one thing to remember is that you can hit the escape key to take you back to your previous position, or Control Enter will take you to your next saved position. Again, this is a high-level overview of how to use IDA for reverse engineering, but it's enough to get you started for later exercises. Now it's your turn to practice with IDA on your own. Analyze the number checker executable and determine the correct input to provide to the key checker program so that it prints the key. Now, let's dive into debugging. We finished covering static analysis, so we'll begin exploring dynamic analysis through debugging. There are common features you will want to utilize when debugging a binary, such as setting breakpoints, stepping into or over instructions, showing loaded modules, the SEH chain, and even memory searching. Common debuggers used for dynamic analysis include WinDebug, OllyDebug, Immunity Debugger, GDB, and even IDA's debugger. When you're debugging, remember that you control what the binary does and how it behaves. You can change the execution flow, you can modify its registers and memory at any point, for example to satisfy a conditional jump or to bypass authentication methods. Feel free to hack your way around a binary in order to get the results you want. To set a breakpoint in your debugger, press the hotkey F2. When you run your binary and it encounters the instruction you set your breakpoint on, then the program will pause. This allows you to analyze your binary further, say to determine the state of its registers or memory at that point in time. When you're ready, you can then resume the execution of your binary. In this example, a breakpoint was set on the following call. When this breakpoint is hit, I can further analyze the stack and its registers. As you see, the arguments were pushed onto the stack before making the call, and you can observe this in the stack window of IDA. If you Google the name of this function call, you can find documentation of this function on MSDN, which is the Microsoft Developer Network. Looking at the arguments passed into this function, we see that the first argument corresponds to a destination, The second argument represents an exchange, and the third argument value is its comparand. By researching function calls to determine their parameters' data types, you can then trace them back through the program. This allows you to then rename the variables to something more meaningful. By analyzing function calls, figuring out their arguments, and filling in the data types allows you to have a better understanding of what those functions are and what type of data it is processing. Let's practice what we learned. Debug number checker and see how you can bypass the key check entirely. Pause here and work on the exercise. When you're ready, resume the lecture for the solution. To solve this exercise, set a breakpoint at the beginning of the main function. When you hit the breakpoint, find where you want to jump to, right-click, and then select Set IP. This will assign your instruction pointer to execute the next instruction, which will then lead you to displaying the key. Most debuggers on Windows are quite similar, except for WinDebug, which uses commands on a command line similar to GDB. Let's cover the basic usage of GDB. Here are examples of basic GDB commands. You can simply run GDB against your program as GDB followed by your program name. You can provide arguments on the command line as shown. To run the application, you use the run command, of course. If you don't provide the arguments on the command line, you can provide them with the run command. You can also execute commands as if you were in a regular shell by using the $sign and enclosing your shell command in parentheses. In this example, we are debugging the binary Linux_debug example. You'll notice we use the -Q option, which is the quiet option of GDB. This prevents GDB from printing the introductory and copyright messages. We then use the run command to execute our application. GDB then informs us that the program exited with a particular error code. The default syntax for GDB is AT&T. To switch to Intel syntax, use the command set disassembly-flavor followed by Intel. To disassemble a chosen function, use the disassemble command followed by the function name. Here are ways to set breakpoints. You can set breakpoints on function names or their addresses. You can always show information about your breakpoints, and if there are breakpoints you want to get rid of, you simply use the delete command. To step into or over instructions, you can use SI or NI, which stands for step instruction or next instruction. Here's a screenshot of using these commands where we're manually stepping through instructions. The key difference with SI and NI is that SI will allow you to step into functions, whereas NI will allow you to step over functions. So far, we can disassemble our binary, set breakpoints, and step through the program as necessary. However, it would be more helpful to view the contents of our registers in memory to determine if they need to be modified. To examine our registers in memory, you want to use the examine command. After the x/, there are three parameters, which are number of bytes, the format to display the information, and in what unit, such as bytes or words, and so on. Here are examples of this command. The first will examine 5 instructions at EIP. The second shows how to examine 4 hex word at ESP, so in this case you're examining the stack. The third demonstrates how to examine a string at an arbitrary address, and here's how to examine 5 bytes of the ECX register. To get more information on your registers, use IR, or IR followed by a list of registers. Let's walk through an example demonstrating the commands we've covered. We set a breakpoint on main and then we run the binary. We hit the breakpoint and examine the 5 instructions at EIP so we know where we are in the function. We then execute the 2 next instructions since those instructions involve setting up the stack frame. We again examine 5 instructions at EIP and we see we're now at the compare instruction. It's comparing some value at EBP plus 8, which is an argument of main, to the value of 3. We look at the value of this argument by examining a hex word at EBP plus 8. We see the value is 1. We continue executing until the move instruction since we don't satisfy the conditional jump. It appears we're now pushing an argument onto the stack before calling the puts function. Let's examine the memory contents at that address. We see that it's the string missing something. Now we know why our program exits because we do not satisfy the comparison where 1 does not equal 3. The program is looking for an argument count of 3, but we didn't run it with that many arguments. Let's see what happens when we pass in additional arguments to the program. As the snapshot shows, passing in 2 arguments represented by the string of A's and B's no longer present the error message missing something. This means our input satisfied the compare, and as a result, the binary executed a different code path. Here's another exercise for you to practice what you've learned. Use both IDA and GDB to determine the input required to print the following message. The disassembly of the first code block is what we walked through in the Linux debug example binary, so you only need to reverse the remaining code blocks. When you're reversing, you may find that you prefer one approach over the other, but doing both dynamic and static analysis will accelerate your understanding of the binary. When dealing with bytecode like Java or Python, simply download an appropriate disassembler and you actually get source code back. It's a lot easier than people think. Through this lecture, you have learned the necessary skills to examine a binary and its sections. You know how to rename and simplify its disassembly. You can convert the disassembly back to source code when necessary. Also, you learned how to analyze and control a binary dynamically using a debugger. Here are some great resources and additional challenges to further your skills in reverse engineering. To get more hands-on experience with reversing, analyze keychecker.exe or the CrackMe listed at the site shown on the slide.